2 days of really exciting talks about the mathematics of deep learning. So if you're into deep learning theory, it's going to be awesome. I'm thrilled to introduce Joan Bruna from NYU to kick things off here. I'm a huge fan of his research. He's done a lot of incredible stuff in terms of training dynamics of gradient descent, expressivity of neural networks. His work on learning single index models is really beautiful. Some cryptographic hardness results that I like a lot. So, probably if you name some area of deep learning theory, he's written a very important paper on it. So we're excited to have you here. Today he's going to talk about diffusion models, I think,
yes.
Which is, to my mind, one of the I was just saying is one of the areas where I think mathematics has really had a tremendous impact on the practice of diffusion models and generative AI. And so, I think studying them is really important. So thank you for coming to Austin and being here, and it's a pleasure to have you. Let's welcome Joan.
Thank you, Adam, for a nice, very generous introduction, and thanks for the invitation. So yeah, I'm going to be talking about some questions involving diffusion models. There's not going to be a lot of neural networks in there, but I guess if you have seen diffusion models, you can see where neural networks would fit in my story. Okay, so this is joint work with Jikun Han, my colleague and collaborator at the Flatiron Institute. And the setup of my talk is really this question that maybe starts from, let's say, classical signal processing, which is solving inverse problems. Okay, so inverse problems, of course, come in many, many domains. For example, in imaging, I have this beautiful picture. I believe it's here in the campus. But maybe I have some observation that just gives me some kind of like corrupted version of this observation, maybe with some noise. Or if you go in many areas of physics, for example, here, like this is like the classical wave scattering problem, where I have the goal of the game is that I have something that I care about, and I observe it through some noisy process, right? And I'm potentially losing information. And so what I want is somehow is to recover the signal of interest, okay, from the information I have. And so one can take this Bayesian perspective of trying to optimally use information, and this amounts to understanding or manipulating what's the posterior distribution. Okay, so assuming that my signal of interest that comes from the world has some prior distribution, complicated prior distribution, now that I have this observation, what I care about is no longer the prior distribution, but the posterior distribution, right, which has been tilted, that has been kind of adapted to account for the measurements I have. Okay, and so in the simplest setting where this observation is corrupted by Gaussian noise, which is what anyone in signal processing does as modeling, you get here this term, this likelihood term here is this familiar Gaussian term, right? You have a quadratic term here in the likelihood. And so also, just to keep it informal, please interrupt me for any question. I want to keep it kind of informal. So this seems like a pretty, let's say, boring, maybe old-style kind of questions. But it turns out that it also is a setting that becomes very relevant these days, right? When we think about fine-tuning or this post-training framework that everyone is now using to manipulate these large language models or big models. Okay, and so here it arises in the following setup. So once I have this big generative model, this big diffusion model, this is typically something that operates by you type a sentence, and then the model produces you some output. And something that I learned recently is that if you do that right off the box, it doesn't really work very well, right? And so here, for example, it's fair to say that none of these images, is really, delivering on what I try to type here. Okay? So what researchers do is this step that they call reward fine-tuning, or guidance, where the algorithm is going to be guided, it's going to be modified, right? So I want to produce samples not coming from my, cool and nice generative model, but I want my samples, to come from a distribution where maybe, I try to increase the likelihood of certain images that I like through this reward function, and automatically decrease the likelihood of getting images that I consider to be bad, right? So in particular, once you do this kind of trick, one gets samples from, like this that maybe look better, right? That people consider them to be better. Okay. So the question here that I'm going to be addressing today is really how can we understand and model the question of how do you sample from a posterior distribution, okay? And the posterior distribution that is defined from a prior distribution where I might have a lot of information, okay? This is really what this study is going to be about. And so, before asking the question of how do we sample from the posterior, maybe we can first discuss about how do you sample from the prior, right? So this is really this framework of generative modeling that has, in some sense, been one of the biggest, as Adam was saying, one of the biggest new surprises or biggest good news of the field, okay? And so now the modern way to perform sampling from a prior distribution is through what we call this denoising, or denoising oracles, okay? And so, but the point is that the point of generative modeling in this framework is to learn a function, a mapping, that is going to take some noisy observation of my data and try to predict the posterior mean. Okay, so try to remove, to try to the best possible estimate to given some noisy observation, try to estimate the clean image. Okay, so this is this mapping is parameterized by two things: the input noisy observation y and t, which is the noise level. Okay, and so this mapping is something that we can very efficiently optimize. We can very efficiently train from the data, because as you know, the posterior mean is a quantity that you can characterize variationally, right? You can characterize the posterior mean as the minimizer of the mean squared error. Okay, this is everyone. This is familiar to everyone here, right? We can characterize this function very efficiently, and this is really one of the reasons why diffusion models are so popular these days, right? As opposed to these GANs or other methods that were very finicky, right? That were very brittle in terms of optimization. Now we have really a problem that where we can characterize what we care about by just a nice old-style regression problem. So how do we sample from this denoising oracle? Okay, so we have this function. What do we do with this function? So this is, again, a framework that was developed, first introduced this very beautiful paper 10 years ago by Jascha Soldikstein and Surya Ganguly and colleagues, and then later kind of popularized by other colleagues in the field. And so it's really starts by a process that takes my original data and adds noise in the simplest possible way. So think about the linear diffusion, right? Which is just going to take my image, consider my image as the initial point of some process, which is just simply a linear diffusion, right? Which is also known as this Orson-Uhlenbeck process. Okay? So if one looks at this, instead of viewing this as an equation at the level of the samples, if you just look at the marginal, like the law, if you track the law of the marginal, this follows a very simple path in the space of measures, and the law of the process really can be viewed as a Gaussian mixture, right? So at the end of the day, what I'm doing is just interpolating clean images with noise, okay? And so the big point that is really behind all this power of diffusion models, here's the kind of the key equation, is that this path of distributions, right, that goes from the distribution I care about to the distribution that I know, which is Gaussian, this path I can move around in this path by applying transport, right? Transport basically means that I can just apply a mapping to my samples, right, and kind of I can move mass around from this distribution to the other. And the key point is that the velocity field that I need to execute this transport, so these transport equations, I can implement them using this function I told you about, right? This denoising oracle is something that I can use to transform Gaussian noise to data, okay? And so this is really a bit of kind of a different framework from before, right? If you think about sampling, and we're going to talk about this later, there's traditional algorithms for sampling, for example, Langevin diffusion, right? This is very, very different. Because here, this transport operates in what we call out of equilibrium, right? We are not just applying a diffusion process until it mixes. Here, this transport is really using a vector field that depends on time, right? It's always out of equilibrium. And also very important, right, maybe for the experts in the room, is that now I have a guarantee for sampling, okay, that is completely agnostic to the geometry of my data distribution. If you're familiar with Langevin diffusion, you know that as soon as the distribution is not log-concave, essentially all the guarantees are out of the window, right? There's nothing much I can say in terms of using Langevin diffusion. Here, this is kind of the thing that really got all the theories very excited about. I don't have this problem, right? Yeah, in some sense, I do have the problem, but it's kind of lurking inside my ability to learn this mapping, right? And so if I have samples that I can estimate this mapping, if I can estimate this denoising oracle, then I can sample efficiently. And this kind of beautiful theory was also introduced, and there's this beautiful paper by Citan, I guess that most of you know, that really formalized all these things. But this is not our problem today. So today we are going to use a little bit this framework, but we are going to study a different problem. Okay? As I said, our problem involves sampling from the posterior distribution. And we are going to consider the simplest possible setting of inverse problem, which are linear inverse problems. Okay? And so just to re-emphasize, I have some prior distribution. And from this prior distribution, we are going to assume that we have learned the perfect diffusion model. So let's say that we have already, I'm already giving you the denoising oracle for the prior distribution. Okay? Now I'm going to have some observation y. That is going to be some linear transformation of my data plus some Gaussian noise. And now what I want is to be able to sample from the posterior distribution, but that I can view as a tilting my prior distribution using a Gaussian, like a quadratic form. Okay, so this is really the posterior that comes from a linear inverse problem. And so I would like to get guarantees for when is it possible to sample from this posterior distribution. Okay, is the setting clear for everyone? Okay. If not, please ask any questions. All right. So maybe there are two questions in some sense. The first one is, okay, is it always possible? Okay, can I always do that? And if, and also the other question is, how do we, design a sampler that has these guarantees? Okay. All right. So, in fact, it's not always possible, and we can use we can use to show this thing that is not possible a very simple lower bound. Okay, we are going to try to relate this posterior sampling problem to a very well-known problem in statistical physics, or even in fact in theoretical computer science, which involves spin glasses. So here, let me try to connect the two things. Okay, so first, let's consider that our prior is going to be a very simple prior. It's just a uniform measure on the hypercube. Okay, so these are all the binary strings of length n or length t. Now we're going to consider a measure on this support, on the hypercube, that is quadratic, right? It's just applying this quadratic tilt to this uniform measure. Okay, so it's almost like a Gaussian distribution, but it's localized, restricted in the hypercube instead of being in RD. So first thing I'm going to claim is that this denoising oracle for this problem is trivial, right? Because I have my prior, in that case, is a product measure. Okay, the uniform measure on the hypercube is a product measure. So the denoising oracle becomes just a scalar. It's separable. It's a separable function that I can write down in closed form, no problem. Yet, if I want to sample from a spin glass, I have a result that in fact is an NP hardness result, right? As soon as the difference between the largest and the smallest eigenvalue of this quadratic form that is defining the likelihood is bigger, are separated by 1, then I have a problem that is NP hard. Okay? And this is a recent result by Delanis, also building from a very beautiful lower bound using the low degree polynomial framework by Tim Konieczny. And we're going to talk later that this threshold, in fact, cannot be improved, right? This is the right threshold for NP hardness.
Joan, do you have an example where pi is not discrete?
Yes. You can actually smooth pi. If you can convolve it with a little bit of noise, okay, you can make it actually polynomial in the end. They're not exponentially small. You can afford some polynomial noise, and the lower bound persists. And I'm going to give you the intuition in 10 seconds. Okay. Let me also say that there was actually beautiful work from here, from UT Austin, Gupta and Eric Price and others, who also kind of realized the same problem, right? The same result, that in fact using this in that case, they used this like cryptographic hardness assumption, the existence of one-way functions, to build basically a protocol, like they built, in fact, some kind of linear inverse problem to show, again, the same thing, right? That you can have settings where the prior distribution has a denoising oracle that can be implemented efficiently, yet sampling from the posterior is hard, okay? And now we come to the, what's happening here, okay? And I said in some sense, there are two properties of a distribution that make it easy to sample. Yes, right? There are two things. The first one is what I told you about log concavity, right? If I have a log concave distribution, right? So a distribution whose energy is concave, then in some sense, we are in the world of convex optimization, right? So you can always have samplers that mix very efficiently. But there's another property that makes a distribution easy to sample, which is tensorization. When the distribution is in fact a product measure, right? Sampling from a product measure is easy, right? You just sample each component and that's it. It doesn't matter if each component is log concave or not, right? It's 1D problem, right? So here what's happening is that when I have a prior distribution that is a product measure, once I apply this posterior problem, this tensorization is completely lost, right? So this is clearly what's happening here, right? When I have a problem like this, I can pretend, in fact, that the prior distribution can be sampled and it's relying on this very brittle property, which is tensorization, okay? And this is why this lower one kind of exists, okay? So the conclusion here is that, okay, we cannot just close the problem and say, okay, that's done. We need somehow this posterior sampling problem is not going to be always possible to do. So when can we do it, okay? And how to maybe exploit the structure in this problem. So for this, let me go back very quickly to this business of transport equations, right? This is what we are going to be using now quite a lot, okay? And so we are going to mostly be looking into two frameworks for linear diffusion. Perhaps the simplest one is just the heat semigroup. So the heat semigroup is just essentially just I'm just going to pump Gaussian noise to my initial distribution, right? And I'm going to have what they call in the business this variance exploding scheme, if you're familiar. Okay? And so the point here of this sampling from the prior distribution is going back to this picture. Okay? So as I said, this denoising oracle allows me to transport samples from Gaussian noise back to my things that look, have the right marginal, right, that come from the data distribution by implementing this reverse transport, right, which depends on this denoising oracle. Okay? But the point here is that this sampling from this prior fundamentally is a two-step process. First step, getting samples from this initial distribution. And second step, apply this transport equation back to pi. Okay? And the point here is that we are going to try to do the same thing. Okay? Now, what we are trying to set up, to posit is that can we try to implement the same mindset, right? The same philosophy. So now, instead of having my prior as my goal, now my prior is my posterior distribution. Okay? So what we are going to try to do is, can we come up with some other distribution, nu t, that is easy to sample from? And once I get samples from this guy, can I use my denoising oracle, right? Remember that this denoising oracle comes from the prior, to transport these samples back to the samples from here. Right? We are going to try to follow this same paradigm, right, of two-step process. So how can we do that? So here's the kind of the key, the main result. In fact, it's not nothing very complicated, right? In fact, it's a very transparent result. Okay? So we are going to set it up in the case of the heat equation, which is this variance exploding, but this is just for simplicity. Exactly the same thing holds for the Orsten-Uhlenbeck semigroup. Okay, this variance preserved. Okay? So here what we are going to define is basically like a path. We're going to really build this one parameter family of distributions, and I'm going to claim that this one parameter family of distribution solves this a very explicit transport equation. So let's see how it goes. So we remember that we define now this nu t, which is a family where I take my phi t, which is the evolution of the prior under the heat semigroup, right? So this is basically, I run the diffusion process on the prior, and I get this family of pi t, right? This is what is here. And then I'm going to tilt each one of these guys by some certain matrix qt, and certain vector bt, right? And these matrices qt and bt, I'm going to tell you that they have to solve this ODE, right? They solve this system of ordinary differential equations. Okay? So this seems like a bit arbitrary. But now the point is that this one parameter family solves a transport equation where the velocity field, if you look at this velocity field, now is something that I can implement in the computer. Why? Because it has two terms. It has the term in black, which is vt, and vt is the velocity field of the prior transport equation, right? So because I know that I have the denoising oracle, I can use transport using the prior measure, right? So this guy is kind of the complicated guy that relies on the denoising oracle. And now what I need to deal with this vector field is just add an affine term which is completely explicit, right? So the point here is that this is something that I can implement. It's not. Okay? So in fact, as a consequence, even more like a user-friendly, like a takeaway, right, is that now what I'm telling you is that if you want to get to this point instead of this point, the only thing that you should change from your diffusion model is the initial distribution in which you sample. In fact, the drift that I have here, right, so this drift that I use in the transport equation is exactly the same. Okay, because again, for the expert in the room, this is what's called like a probability flow. You can write it as a Fokker-Planck equation by having the score of this guy, and the score of this guy is going to absorb the modification, right? And you are left with exactly the same drift that you had in the prior. Okay, so the point is that I have exactly the same, in terms of posterior sampling, what I'm saying is that the only thing that you need to change is the initial distribution. The rest, you choose the same transfer. Okay. And just to show you why this thing is actually, there's nothing really profound, there's really nothing very complicated there. We can just do the proof now together, right, in one slide. Okay? So we start from the linear diffusion, which is this heat equation, right? As I said, it solves, so we get this kind of VT that we had before, and we can just do a change of variables, just derive the evolution for the potential, which is taking the log, and I guess maybe some of you know, right? Is that if you do that, you get this Hamilton-Jacobi equation, right? That is satisfied by the potential, and so now we just verify the ansatz, right? We just now, we define this nu t. We just compute the time derivative of nu t. You get a bunch of terms, right? Some of the terms, that depend on the qt and bt are in blue, and the other terms are in red. Okay, so you get a bunch of things. And here you get the partial derivative of the potential, which because it solved the Hamilton-Jacobi equation, you can replace by these guys. Now that we have the time derivative, we compute now the advection term, which is like the right-hand side of the equation. Okay, and we verify. We just substitute exactly with we just directly compute these divergences, and you expand. And at the end of the day, what you see is that you get basically the terms, the red terms cancel each other, and the blue terms cancel each other because I just ask them to satisfy this ODE, right? This is where the ODE comes from, right? Just because I want to cancel the terms. So there's really only one step that is kind of magic here, which is that some cross terms here, right, cancel each other, okay? And this is where the fact that we are looking at linear inverse problems is completely instrumental, right? Because the tilt that we are applying is a quadratic function, you have this magic happening, right? Where the terms that would be bothering you just disappear. Okay, so key takeaway here is that this only works for linear inverse problems. But linear inverse problems, in fact, are quite interesting, right? I mean, they really have a pretty good range of applications. So it's not completely stupid. Okay. So there are two things here that natural follow-ups is that I intentionally didn't tell you. I wrote this nu t, capital T, right? That's the starting point of the measure. I didn't really tell you what is this capital T, right? In diffusion models, if you know, we typically run these diffusions for as long as we can, right? Just because we get closer and closer to the Gaussian measure. Can we do the same thing here? right? Or what is this capital T? And then, very naturally, I mean, I told you that we have to sample from this initial distribution, nu capital T. When is this something that we can do efficiently? So let's look at the first question, okay? Until when can we run this equation? So this, remember, is this equation that I wrote before, this ODE, which is called the Riccati equation, right? It's a quadratic ODE, okay? Because these Q's are Gram matrices, right? The Q is basically the auto product of the measurement operator with itself, right? So we have a PSD matrix. So this equation becomes a 1D equation where we just need to evolve each of the eigenvalues of the initial distribution, right? And if you solve this, so this equation can be solved explicitly. And you see that it has this slightly disturbing behavior, is that it has a blow up in finite time, right? So this equation, basically, you start here, and you keep running, and then boom, it completely blows up, okay? And it blows up, as you can see here, explicitly, you can perfectly predict the time in which it's going to blow up, okay? So what it means is that we cannot run it forever, right? We can only run it until the first eigenvalue blows up, right? Because as you know, I mean, this thing is completely monotonic, right? So the time of blow up is going to be determined by the largest eigenvalue of Q, okay? And so the blow up is at this exactly at the 1/2 of the inverse of the norm of Q, right? This is an important parameter. And now if we can look at this quantity and we plug it back in our posterior, so this is the posterior that we can, this is as far as we can run this equation, right? At blow up, we get this measure, which is, we have run the heat equation up until capital time T, and then the tilt at this point, right? If you just replace exactly this quantity at Qt, in fact, you can write it more conveniently as the inverse, right? So the inverse of Qt, in fact, is Q minus 1 minus some multiple of the identity. This seems a little bit strange, right? That I have this kind of tilt at blow up, which I can write it quite compactly as the inverse of something. So what does this thing kind of tell us, right? I mean, when you have a quadratic tilt, like e to the minus some quadratic form, and I have some information about the inverse of this quadratic form, this is an object that has a certain status, right? Like the inverse of something that I put in the quadratic tilt has a status of a covariance, right? If you think about the Gaussian, right? Like it's a quadratic form, and the matrix is the inverse of the covariance, right? So maybe we can try to interpret this quantity as the covariance of something. And in fact, this is in fact exactly what's happening. So this is the right way to think about this process is using a framework which is called the Polchinski semigroup, right? And this is for those of you who are familiar with Ronan Eldon's stochastic localization, this is really exactly the same thing, okay? But in a slightly more general framework that we need here. So this was developed by actually my colleague Roland Bauerschmidt, and then Thierry Beaudineau and Benoit Dagallier like a few years ago. And so let me just very briefly give you the kind of the main ingredients. So the point is indeed that this measure that we arrived at, in fact, can be obtained by running the Polchinski semigroup over the original posterior. Okay? And the way this semigroup operates is actually pretty nice, pretty natural. Is that I have some measure at the beginning that I can really decompose into some field that has some covariance, right? Times something that is kind of the non-Gaussian component, right? And this is something very used in physics a lot, right? When I have some energy function, and I can separate into like the Laplacian term, which is kind of the Gaussian component, and then the non-Gaussian term, which is kind of these local interaction potentials, okay? If you have seen about these like double well potentials and these 5-4 models, these are exactly where this thing comes from. Okay, the point is that I can look at now the quadratic term, and I can view it as I have some covariance, originally my process, and I can try to decompose my covariance, right? I can write down this matrix, if you want this PSD matrix, I can write it as an integral of tiny covariances, right, that I kind of just adding it each other, right? As you know, Gaussian covariances have this very nice property, right? It's that if I have the sum of two Gaussian processes, right, that are independent, the covariances is the sum, right? So really you have a semigroup structure in this covariance. Okay, so I can look at the covariance and decompose it into tiny covariances. And so now if I stop this decomposition at any given point in time, I just accumulate the covariance from 0 up to time t. So now what I have is that if I just apply this covariance decomposition in my measure, right, the original measure that has some kind of initial covariance and then some non-Gaussian part, then this is a measure, right, that is really some, you know, I have obtained some. I have used a little bit of my covariance in the non-Gaussian part, right, through the heat semigroup, and I have some remaining covariance, which is the one that I haven't integrated yet. Okay, and this framework is something that they used in this paper. They use it to actually get functional inequalities, right? So to try to get this log sub LF inequality for complicated measures. Because they use this kind of covariance to decompose the entropy. Here we use it in a completely different setting.
Joan?
Yes?
I mean, how does this work if the original measure has like terrible condition number or something?
Yeah, so good.
Where do you pay for that?
You're going to pay exactly where we are paying, as you can see, right? Is that if this thing has actually terrible condition number, so okay, let me first say is that this framework that they developed, right? In fact, can work for very general covariance structures, even when they are not isotropic. For example, if you think about a very natural place where you can think about this framework is modeling images. But now instead of modeling images with finite pixel grid, think about modeling the field, right? Like images where the resolution just keeps getting smaller and smaller and smaller and smaller, right? So this is an example where the covariance, you cannot just assume that it's flat, right? Because it doesn't integrate, right? You have some kind of correlation, right? Length that is like intrinsic to the field. This is where you need to be very smart in kind of decomposing the covariance in the right way, right? To actually keep it like this, okay? In our case, the limitation comes from a slightly different setting, right? Is that we have the denoising oracle that has been trained using Brownian motion, right? Which is completely isotropic, right? Our denoising oracle has no idea about their preferred direction. So what it means is that we are forced to use a decomposition, a flow that is isotropic, right? Our decomposition, our Polchinski flow, really can only use covariances that are isotropic. This is because the denoising oracle that we have is what it is, right? We cannot change it. So we basically can only run this flow as long as the remaining covariance is PSD. And this is where we pay by condition number, right? Because as you can see, the better the condition number of this thing is, the longer we can run the flow. And let me also say that this observation, right, that we can, decompose the covariance to get better sampling, is also something that was done essentially the same week as us by Yu-Shin Zhu and Andrea Montanari in a very also nice paper. In their setting is based on they're motivated by problems in sparse inference, which is slightly different from us. Okay, so now next thing is how are we going to sample from this? How are we going to sample from this measure nu t? So we are not going to do anything fancy. We are just going to use the off-the-shelf sampling algorithm that is Langevin dynamics. Okay, we are not going to try to do anything weird. So, okay, so we first we verify that we can use Langevin dynamics here. We can do it because we know the score of this nu t, right? The score, this is the drift that you need in Langevin dynamics. You need to know the gradient of the potential, right? So in our case, the gradient of the potential here is a term that is quadratic that depends on our qt's that we know, plus the score of pi t, which obviously we know because we know the denoising oracle, right? We know the score of the prior, right? So we know the drift of this SDE, so we can run it. When is Langevin dynamics going to be sufficient for us? Again, we are just going to use like standard things here. We are just going to exploit or wish for the fact that this nu t is log-concave. So that Langevin dynamics is going to mix efficiently. So this is obviously this well-known Bakri-Emery criterion that I guess tells you that if my Hessian, right? So if the Hessian of the score is always positive definite, right? Like quantitatively positive definite, then I can relax, this dynamics relax very fast, right? In a way that there's nothing hidden, there's no dependency of dimension or anything, right? This is a very standard result. Okay? So the Hessian in our setting is the Hessian of that we have from the prior, plus this Qt that we just built. Okay? All right. And so if you just collect all these things together, we just need to verify when this Hessian is going to be PSD. So there are two components in the Hessian, right? There's the first one that is this matrix Qt that we just computed explicitly. And then we have this Hessian of pi t. So pi t, remember, that is you take the original measure pi and you convolve it, you add Gaussian noise, right? So this becomes a Gaussian mixture, right? You just add noise to your distribution, right? And so we have many, many results. There's a lot of structure coming from Gaussian mixtures that we can use to compute the Hessian, okay? So if you use the result, if you use the standard computation for computing the Hessian of a Gaussian of mixtures, what you see is that the object that appears is something that in physics they call the susceptibility, right? Which is basically you look at your initial distribution, you add Gaussian noise, right? So this is an isotropic tilt, right? So you add Gaussian noise, and you look at the covariance of this measure, and you look at the operator norm of this measure, right? So it's a little bit, there's a lot of steps here, but the essence, right, is that by just looking at covariance norms, right, we can control many things about mixing time, right? This is one of the strengths of Eldan's stochastic localization, right? That everything is boiling down to computing covariances, right? Which is much, much, much easier than computing spectral gaps, okay? And so the point is that we arrive at this very user-friendly condition, right? Where it says that, okay, if I look at the susceptibility of my prior, and I evaluate the susceptibility at the norm of Q, if this susceptibility is not too large, in the sense that it's upper bounded explicitly by the condition number of my measurements times the inverse of the norm, then then my measure nu t is strongly log-concave, which means that the whole scheme just works, right? So I can just get a posterior sampling by first sampling from nu t, and then running the transport equation back. Okay? So obviously, because we are using tools that are, as I said, very, very completely related to these ideas from Ronen and this Polchinski semigroup, this susceptibility, as I said, is really kind of the central object in these localization schemes of Yuan Shen and Ronen Elda. Okay? Oops, sorry. And just to give you like a sense of how this thing actually behaves. Oh, okay, this is an important equation that is kind of hidden here. So I guess the point is that for distributions that are not too weird, right? Think about like a generic non-log-concave distribution as a distribution that is confined in the sense that if you look at very, very far, it is actually log-concave. But inside a certain ball, it can do weird things, right? But it's smooth. So in this class of distributions, then the susceptibility is at the scale 1 over t, right? So this function is really of the order of 1 over t. Okay? That's the point here.
I have a question. So
sure.
You use inequality in proposition to control the time, like the iteration you can run or something.
So the time until we can run it is actually this guy here. This is 1 over. So remember that the time t was actually 1 over the norm of q, right? So
I just wonder what you use inequality for.
This inequality?
Yes.
This inequality is really just controlling the fact that the Hessians are positive definite everywhere. This is where the inequality comes from.
So do you need to compute the inequality every step?
No, just once. It's just at this point. It's really this is a guarantee that then is gonna imply that the things is actually you only need to have log concavity at the end point at nu t, capital T, right?
But if I run past the point where the inequality is satisfied, what happens?
Oh, then we cannot tell you anything. If you run the equation for longer, right? Then actually, in fact, you cannot run the equation for longer because you have one eigenvalue that is just blowing up to infinity, right? So you need to restrict. It's almost like you have a matrix, and then one direction has become completely singular, right? So the measure has become singular in one direction. So yeah, a priori we cannot run this equation for longer.
No, so I assume that t equal 1 over
yes
1 over normal q, and you always run up to that point. Then why you need this inequality? why at the end we need to check this inequality?
Yeah, because okay, so if at the end you get the sample nu t, you get the measure nu t. If this measure is not log concave, then you don't know how to sample from it.
Oh.
Well, I mean, you could hope, right? You could just say, okay, I'm gonna just you can have a different algorithm maybe to sample from non-log concave distributions, right? That uses some structural property. But here we just choose to use something that is going to work all the time, right? And then we just impose something that is a bit stronger. Maybe that is the fact that it's log concave.
So just for understanding, so if I run 1 over q and I check this inequality and it's not satisfied, then I just run over 1 over 2q and double check, and 1 over 4q and double check. Is that correct?
You mean to run it for less time?
Yes, less
No,
time.
no. If you run it for less time, as I'm going to explain later, there's less chances that it's log concave. So the bottom line is that you should run it for as long as you can, right? And you can see, because what happens when you move in this path? Your pi becomes nicer because it's convolved with more and more noise, right? So it becomes closer and closer to Gaussian, nicer. And your matrix Q becomes more and more concave. More and more convex, right? All the eigenvalues go up, right? So you take a Gaussian and you multiply it by something that is even more log concave, right? So you should definitely run the equation for as long as you can. Anyway, we can maybe continue, take it offline.
Thomas, do you have a question?
Yes.
Thank you. I'm sorry. So is the following picture correct? When the time converges to the critical time, the largest eigenvalue of Q blows up,
Yes.
which means that the contraction rate of the noise in the corresponding eigendirection acting on the probability distribution is forcing it to concentrate.
Exactly. It's in fact it's a good thing, right? Because in fact it's very, very localized. It's very, very, very confined, right? In fact, until it collapses in one direction.
But if you project out that direction,
Yes.
the other directions could still keep on contracting.
Exactly. All the eigenvalues actually grow. So if you look at the equation of Riccati, everything just contracts a little bit, right? The problem, of course, is that this base measure, right? It starts from a completely weird location, right? So it gets better, it gets nicer, but the only control that you have is really coming from this. The only way where you can guarantee things is that if the Hessian is positive, definitely. Okay, so I'm running a little bit out of time. I guess I have 5 minutes, maybe.
Sure.
Okay, so very quickly, again, this is maybe for the experts in the room, right? But someone would say, okay, look, at the end you have just transformed the problem of sampling the posterior to a problem of sampling from another posterior, right? And you are telling me that I could just use Langevin in the final point. Why not use Langevin in the original point, right? So somehow this comparison is valid, right? It's something that I owe you. So the point that I'm going to make here is that, nu t, and then related to what you're saying, is a nicer distribution. It's more log concave than mu, right? Even this thing is actually a bit informal. And one way maybe where one could quantify it, ideally, is to look at the LSI, like the log-Sobolev inequality associated with nu, and compare it with the log-Sobolev inequality associated with nu t. Okay, that would be ideal. The point of course is that we don't have tools to compute the LSI directly, right? The only thing that we have is to compare bounds, right? Upper bounds of LSI. Okay? So here that's the best thing we can do, right? We can just compare the lower bounds of the two things using the tool that we believe is kind of the sharpest, is going to give us the sharpest possible thing, right? And so indeed we use this Polchinski flow to compare the, give like lower bounds of the LSI. And the point is that, there's this decomposition that we can use, and we get basically to two lower bounds for either nu and nu t. And the point is that these lower bounds, in general, as you can see, that the lower bound associated with the over tilted posterior, in fact, it's better, it's always bigger than the lower one associated with the original posterior. Okay? So the point here, I mean, this is kind of a soft argument, is that the nu t is more log concave than nu, right? So the algorithm is doing something that's slightly non-trivial. Okay. But also to show that there's no magic either, right? I mean, what we are, at the end of the algorithm, in fact, is just piecing together things that, in our minds should work, okay? So let's go back to this equation that I just gave, that is the sufficient condition, right? And there's a, as I said, there's a kind of different things going on here. There's on one side something that depends on maybe the geometry of the distribution, right? This susceptibility. Then something that depends on the norm of Q, which is, remember, is a signal to noise ratio, right? It's like the more noise I have in my measurements, the smaller the smaller the norm of Q, and then the condition number of my measurements. So we can draw this phase diagram, assuming that we are in this kind of standard setting where my measure is confined and smooth. So this is at the scale of 1 over t. We can really check when this equation is satisfied, and it's basically satisfied in this green region, right? When so here I have the condition number on the y-axis and the signal to noise ratio on the x-axis. So there's one regime that is first natural, right? Is when I have the condition number that is very small, that is of the order 1. The right-hand side blows up, so I'm in the condition where this thing is satisfied. So this is not very surprising, because when my inverse problem is very well conditioned, in fact, my operator is not very different from a denoising operator, right? Denoising operator is the extreme case where the condition number is exactly 1, right? Obviously, if I have the denoising oracle, and I'm asking you to solve a denoising problem, well, I mean, I guess it would not be like the biggest surprise of the year that I tell you that it's possible, right? So this is really what happens here in this regime. Then I have another regime where I'm in the lowest SNR regime. Is this region where it doesn't matter the condition of the problem. If the norm of Q is small, then this is also going to be satisfied. And this is because in these situations, my measurements carry very little information, right? I have a lot of noise in my measurements, right? So the posterior, in some sense, is not very different from the prior. So again, if I know how to sample from the prior, I should be able to sample from the posterior if they are not very different, right? Maybe you can use these tricks like important sampling and things like that. Well, here the nice thing is that it's exactly the same algorithm. It's going to work out of the box. And then the last thing is in this region, right? In this region, what I have measurements that are very high quality, right? The signal to noise ratio is very, very, very high, which means that I have very little noise in my measurements. If you go back to the equation, what happens with the Q at the initialization is already a matrix that is very, 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 very concave, very convex, right? So this makes the whole measure initially log-concave. Okay, so again, here, because nu is already log-concave, nu t is also going to be log-concave. And again, it's exactly the same algorithm that we use in all these regimes that kind of connects, like glues together regimes where you would expect this problem to work. Okay, and just to maybe quantify things a little bit, let's go back to Ising models. Okay, and let's try to see what would happen in Ising model. Okay, so again, we decompose the measure as the uniform of the hypercube and then over Q. So we can, because we are in the hypercube, we can add or subtract an identity to the matrix, right? Because the measure is constant, right? And the norm of X is always constant. So we can assume that the smallest eigenvalue is 0, just for simplicity. Okay, so the norm of Q becomes this difference that we just saw at the beginning, right? The difference between the largest and the smallest. So then, using the fact that the susceptibility for this uniform measure is always 1, independent of t, we get that this condition is true as long as the difference between eigenvalues is smaller than 1, which is exactly the threshold that we just saw. Okay? So in that sense, this posterior sampling algorithm does as well as it can possibly be for this problem, right? So the algorithm, in fact, is not completely stupid. Okay? Again, there's no magic here. There's no big breakthrough, because we already know how to sample from these Ising models using, in fact, global dynamics, which is basically Gibbs sampling, right, on the hypercube. Okay, and this is also nice work by Anari, and also Ronen and Yuanzi have nice papers. The different thing here is that this global dynamics is, of course, a much simpler algorithm. But to show that it can sample from this measure, you need a little bit of non-trivial extensions of this Bakry-Emery criterion, right? Using these kind of decompositions of entropy and so forth. Here, on the other side, we have an algorithm that is maybe less straightforward, is maybe less clean, right? There's this two-step algorithm. But then the analysis is very easy. It's just Bakry-Emery, right? So it's basically, in one sense, you have nice algorithm, hard math. In the other side is the opposite, right? It's like a slightly less clean algorithm, but much easier analysis. Okay, I have some things, but maybe I will skip in the interest of time. This is for SK model. Maybe if someone is interested in SK models, we can discuss offline. I also want to mention just briefly that indeed someone was asking, I think before, right? What happened when nu t is not log-concave, right? It can happen. So the point is that people have, this is a problem that is very important, right? This posterior sampling or manipulating diffusion models. So there's a lot of heuristics, right? There's a lot of things that people have developed, like this guidance or modifying these vector fields that people use in many imaging applications. So the point is that if you can use these tricks in this nu t rather than nu, right? This posterior is in fact some sense nicer, right? If you do these kind of tricks, it generally gets a little bit better, right? So this is the example where if you do the tricks in the posterior, in the tilted posterior versus in the original one, you get a little bit improvement. But again, these are all like this is just numerical, right? So we don't understand why this thing happens. And then for Gaussian mixtures, you can show that this thing actually does work very well. So just to summarize the question here that we studied, is really this question of using the power of these diffusion models to problems that maybe is arguably more interesting in physics, so in science and many applications, right? To sample from a posterior, right? Than sampling from just the prior out of the box. So this problem, in fact, is not as trivial as one could hope, right? Many of the guarantees that we have for prior sampling just become obsolete when it comes to posterior sampling. So here we just look at the linear setting, right? Which is a very kind of the simplest, the first place to start. And so one of the things that we are now working on is to extend this framework to nonlinear inverse problems. And so nonlinear inverse problems require a completely different approach that we are using annealing schemes for that. And so, I guess that's everything I wanted to say. So if you're interested, there's this reference here. And then thank you very much for your time.